All right, so good morning and welcome to the EE2040 course. Let's get started. And last week we started looking at feedback amplifiers. We looked at the feedback concept, in general what feedback means and how it improves system stability and many other properties at the cost of the gain. We said we achieve a lot of good things like stable parameters, larger bandwidth, and many other things, input output characteristics like input impedance and output impedance the way we want it. We achieve all this by trading off gain. So, we reduce the gain, but we achieve many other things, low noise and things like that. And also we looked at the 4 feedback topologies, one each for each of the amplifier topology like voltage amplifier, current amplifier, transconductance and resistance amplifier. So, for each of these amplifier, depending on whether your input is a current or a voltage and output is a voltage or a current, the way you sense the output and you mix with the input feeding back will be different, and accordingly we had 4 such topologies: series shunt, series, shunt series and shunt, right. So, those were the 4 topologies that we looked at, and we drew the topologies and also we wrote down expressions for the closed loop gain, input impedance and output impedance when you close the loop. So, voltage gain with not voltage gain, so the gain can be anything. So, gain with feedback or closed loop gain, closed loop input impedance with feedback and output impedance with feedback. We wrote expressions in terms of the amplifier quantities without feedback and 1 plus beta A. You either divide or multiply by 1 plus beta A to obtain the feedback with feedback properties, right. But we did not derive them. So, today let us start with a very short section where we derive these things that we said those are the values for one topology we will derive and will apply to the other things as well, right. Should be able to derive for the others, right. So, any questions so far before we get started? Okay. So, let us get started then. So, I am going to use this series shunt. What is series shunt? You mix in series, sample in shunt. Mix in series means it should be a voltage, that is why you add 2 voltages in series, right. So, it's a voltage input, and sample in shunt meaning that you put the probes in parallel to the output, which means it should be a voltage. So, you use a voltmeter in parallel, right. So, this should be a voltage in, voltage out, that means a voltage amplifier. So, this is a voltage amplifier. So, we call this voltage amplifier with series feedback, voltage series feedback amplifier, right. So, if you start with the amplifier without feedback, right. So, what we are going to do is we are going to work with equivalent circuits. We are not going to draw transistors and things like that. We know whenever we have it can be large number of transistors, maybe multi-stage amplifier, whatever it is, as long as it is linear and it is operating in the linear range, you can represent it using a Thevenin's equivalent circuit or some amplifier model, right. So, the amplifier model for the voltage amplifier would look something like the way we had was input represented by a input impedance Ri without feedback, and then you had a Thevenin's equivalent circuit to represent the voltage, right. So, this is basically A times, so this is, since this is a voltage amplifier, you can write AV times the input here, right, AV times V in, V in, and this is R out. So, that is the amplifier without feedback, And then what is Vi? This is Vi. Output is V out. So, that is where we started, and often this is connected to a load RL, and this is connected to a source. Let me, for this instance, I am using an ideal voltage source Vs, but now since we have negative feedback, this is a feedback resistor, we modify this. Now, what we sample is the output. So, therefore, we connect something in parallel. If you connect a very high input impedance voltmeter, nothing would change in the output side. So, it is basically this would be V out. This is what I gave to the feedback network. I am not going to write that, draw that feedback network. I do not need that part. I can totally omit these two wires, not connected to anything actually. But I have represent the feedback with a another voltage source, but it is a dependent voltage source. The direction is like this. This is Vf, the feedback voltage, right. So, it should be the same direction as this, so that this is equal to Vs minus Vf, okay, and this is equal to beta times V out. This is V out, right. So, this is my equivalent circuit. Now, if you look at this whole thing, like this is my amplifier with feedback. This is the amplifier with feedback, right. So, like we have characterized this amplifier without feedback with AV, Ri and R out, we need to characterize this amplifier with feedback with the three quantities AV with feedback. So, we call this ACL, closed loop gain, RIF, R out F, where RIF is here, R out F is this, correct. These are my parameters. Load current flows like this, I out. Input current goes in like that. Okay. Right. So, let us try to find each of these parameters for the modified version. Let us start with input impedance. Input impedance with feedback. how do we define RIF? Input impedance, this voltage divided by that current. This voltage divided by the voltage input to that feedback amplifier divided by the current drawn by it, right? That is Vs divided by II. But we know Vs is equal to, I can use the Kirchhoff's voltage law to find that voltage, is equal to this plus that. This is equal to beta times V out, Vf. Vi is equal to II times Ri. Okay. So, therefore, I can write Vs is equal to II Ri plus Vf, which is equal to II Ri plus beta V out. But V out is equal to this voltage here, that is equal to this voltage minus the voltage drop across that resistor when there is a current drawn. If you do not have a load, that will be the open circuit voltage, that will be equal to AV times Vi, right. But now it is connected, so let us write that as AV times Vi. This voltage will be the voltage division between R out and RL. So, therefore, this has to be multiplied by RL over RL plus R out, correct. So, that is my expression for V out. I can replace Vi with this expression I times Ri. So, I have, let us call this AV dash times Vi, right, AV dash times Vi, but Vi is Ri times AV dash Ri II, where AV dash is AV times this quantity over here, RL that is your AV dash. Let us define it like that. So, input impedance RIF, which is basically Vs over II, which is equal to Vs, that is this expression, which is this, we can replace V out with the expression here, right. So, therefore, II Ri plus Vf, which is beta times V out, which is AV dash times Ri times II divided by II. So, you get rid of I and you end up with RIF equal to, I can take out Ri 1 plus beta AV dash, 1 plus beta AV dash, right. Now, our expression was 1 plus beta AV, not AV dash, correct. The expression I gave you last time for the voltage amplifier was 1 plus beta AV. Where does this AV dash come? That comes because you have now loaded it. The one that I have gave earlier was for the unloaded condition. But let us see whether if this becomes 1 plus beta AV when we unload it. What do you mean by unload it? That means you make RL go away, RL equals to infinity. Okay? If you remove RL, that means you remove the load, so that is open, so the open circuit. So, limit of AV dash when RL goes to infinity, that is basically removing this, right, is equal to, what is AV dash? AV RL over RL plus R out AV limit AV 1 plus R out over RL, RL goes to infinity, that becomes 0 and this becomes AV. Yeah, right. So, when that happens, RIF, when RL goes to infinity, this goes to RI 1 plus beta AV, right. So, it is the same thing. The thing to remember though is, if you load it, you can load the thing, you can get the expression and load it later, and then you can think that the expression would be so you need to ensure that if you are loading it, this AV is the loaded AV, okay, not the so then you have to multiply it by RL over RL plus R out, you need to keep it in mind. So, as long as your input is represented by this Thevenin's this voltage, right, input is a voltage, that can happen either in this case or as well as in transconductance amplifiers, right, input is a voltage. Both these cases RIF has the same expression because there is nothing to change. The only difference is, instead of beta AV you might have beta GM, where GM is the gain of the transconductance amplifier. That is the only difference, right. So, that is correct. The next thing that we want to find is closed loop voltage gain. ACL. How do we define ACL? Output of this feedback amplifier, that is V out, right. So, this is basically the voltage appearing here, V out is the same thing, there is nothing in between, and the input here, that is Vs, right, V out divided by Vs. So, what is V out? Now, let us work with unloaded case here, unloaded case. Okay. So, let us say RL is much bigger. Okay. So, this is unloaded compared to R out, it's unloaded, not unloaded. So, this is equal to V out is AV times Vi. If there is no current, we can easily change it. Instead of AV, if you use AV dash, it will give you the loaded condition, right. It is just a matter of changing AV dash for AV, right. So, it is not difficult, everything will be the same, but let us work with this unloaded condition, because we know now by taking RL to infinity we can obtain this. So, let us just work with that condition. Okay. Understand why we are removing it? Okay. If not, all what we change is whenever you have AV, you just put AV dash, right? That's the only difference. Divided by Vs. What is Vs? Vs is equal to this plus that, right? That is Vf plus Vi. So Vi, Vs is Vi plus not Vs, I times Vi. So Vs is equal to Vf plus Vi. But Vi, since output is Vi times AV, Vi is V out divided by AV. Or Vf. So let's keep it in Vi, in terms of Vi. Vf. So I'm keeping Vi. I'm not changing Vi. Sorry. So we can, instead of Vf, what is Vf? Vf is beta V naught, right? Beta V naught. So this is AV Vi plus beta V out, beta V out. That's also equal to AV Vi divided by Vi plus V naught is AV times Vi, right. So beta AV Vi. So therefore, you can get rid of Vi terms and you end up with A closed loop is equal to AV 1 plus beta AV. That's the expression that we had last time. Keeping in mind that this is for an unloaded condition. What happens if you load it? Will it be just this multiplied by RL or RL plus R out? Can you write it like that? No, you can't, because there is this AV term also. So therefore, if you want to find the loaded condition, that would be ACL dash, which is equal to AV dash divided by 1 plus beta AV dash, where AV dash is equal to AV RL over RL plus R out. Okay? We need to keep in mind. Right? So, two down. One last thing to find, output impedance. ROF. Let's define ROF. Output impedance is V out over I out. If you can go back and remember, this is not just it. This has to be when Vs is equal to 0, right? Only when it is defined like that. So, if you quickly draw the circuit corresponding to this, that would be a short circuit here. Rest of it will be the same, right? Rest of it will be the same. But now, we don't have this RL. How are we going to, if you don't have a source here, if you short circuit this, output will be 0 current and 0 voltage, right? Isn't it? So, how are you going to measure it? So, what you do is you actually remove this resistor, connect a source. It can be a voltage source or a current source, and measure the other thing. If you connect a voltage source, you measure the current. If you, so that is, you connect a voltage node voltage source V out and measure the current I out, or you connect a current source I out and measure the voltage V out. Either way is fine. So basically, what you will end up having is something like this. Okay. So this one is V out, and the current now will be going into this I out, this is R out, this is AV times VI, this is VI, this is VF, RI. That is the circuit now I have to work with. What is the feedback signal? That is my feedback signal. That is V out. Okay. So what I am trying to find out is the input impedance looking into this. So I out is basically, I can write the expression for I out is equal to this voltage applied across this. So that is this voltage difference divided by R naught, right. So V out applied voltage from external source minus AV times VI, this voltage divided by R out, and Vs, the other, so Vs is now 0. If I apply the Kirchhoff's law, so Kirchhoff's voltage law to this circuit, I know that Vi plus beta V out, which is Vf, is equal to 0. So therefore, Vi is equal to minus beta V out. So therefore, I can replace this Vi with this expression for V out. I am going to apply it here. That is equal to V out minus AV times minus beta V naught divided by R naught. So this negative sign with this we will have V naught 1 plus beta A V divided by R O. So from this I can obtain the expression for the output impedance from the definition. Therefore, V out over I out is equal to this V out divided by this I out is equal to R naught divided by 1 plus beta. That is your expression. Okay. So that is your expression for in output impedance. Okay. So hopefully now with this derivation you can always go and derive the same expressions that we have written down last time for the other configurations as well, right. So it's easy. Okay. Right. Now let's look at now the next thing is to basically go to a problem, but in addressing a problem, okay, there are a few things that we need to write down, but we'll do it within the problem itself, right? So while seeing how we are going to solve the problem, we'll introduce some theory as well, right? Okay, here goes. So we have a two-stage amplifier. So biasing of the first stage, two NPN transistors. This one has an emitter resistor. This is a common emitter amplifier stage, but with a emitter resistance, which is capacitively coupled through a resistance to a source. And the second stage again is AC coupled, so that output of this is coupled to the next stage using a capacitor. Again you have a coupling biasing stage and an NPN transistor. Again you have a emitter resistor. And this is also a common emitter amplifier stage. So you have two common emitter amplifiers connected like this. And the output, and there is a bypass capacitor across this second stage, but not the first stage. Output is taken from the collector of the second stage through a capacitor. So this is the output. We have an output. You may have a capacitor output, that's okay. But now this is powered by plus VCC and grounded here. This is a circuit without feedback. Now the difference is we are going now if I give you this circuit, you should be able to do the DC analysis for first stage and the second stage separately, find out their operating points, then make sure that they are within the linear range, that is linear active region, not saturated or cut off. Once you verify that, what you can do is draw the AC equivalent circuit of this by short circuiting capacitors, open circuiting inductors where we do not have any, and replacing the VCC with a ground, right. So, it is basically voltage source is grounded, short circuited with replaced with its internal resistance. And then you replace the transistor with the suitable model, maybe H parameter full model, maybe a simplified model, and then it is just a circuit that you need to solve. You can find all the required quantities, input impedance, output impedance, and the voltage gain. Once you can do it, it would be very similar to what you had earlier. It is just a Thevenin's equivalent kind of amplifier circuit with input impedance, output impedance, and a voltage gain, and then you are done. But the new thing here is that now you have feedback. The feedback is connected like this. You have you take it from the output side, connect it through a capacitor and through another resistor to the emitter of the first stage. So, this red color one is the feedback circuit. So, you take something from outside and feed it back into the input. Right? Is this the input? Is it input or is it output? Is it the output of the first stage, or can you consider this as an input? We will see. Right? Let's have a look at it. If it is not clear at this point, that's okay. Right? So, we have these parameters. We have Vs, and we have the current, input current II. Input voltage at this point is this Vi. Okay. That is the input voltage. Output current is this I. That is the current that flows through the collector, that is the output current. That is I. Output voltage is between this and that, V out. That is your output voltage. You can put a capacitor if you want, that is fine. And let me give some values for these. This is 100 ohms. This one is 200 kilo ohms. And this is 200 kilo ohms too. So, sorry, this is 22 kilo ohms. This is 22 kilo ohms. This is 100 ohms and it is not bypassed. There is no bypass capacitor. This one is also 22 kilo ohms. This is 220 kilo ohms, that is the second stage biasing. This is again 22 kilo ohms. RC for the second stage is 4.7 kilo ohms. This is 1 kilo ohm. And this feedback resistor is 10K. Okay, so if you want, you can call this RS. I don't know if I have used any. I haven't used any notation there, but let's say R1, R2, RC1, RE1, R3, R4, RC2, RE2, and this is RF. Additional information is given. HIE is equal to 1.1 kilo ohms. HFE is 50, that is beta. HRE is 2.5 times 10 to the minus 4, and HOE is 1 over 40 kilo, right. So, these are the things that you have. The two transistors are identical, right. So, in solving this, the first step I said was identifying the feedback network. The feedback network basically in this example consists of this resistor RF in series with this resistor RE1. Okay. So, the feedback current goes through that in series with this 100 ohms resistor RE1. This 10K resistor is RF in series with RE1. Okay. So, we have identified the feedback network. Number 2, this is number 1. Number 2, if at the output side feedback network is connected to the output of the circuit directly, then name it as voltage, or in other words shunt sensing. Else current. Network is part of the output circuit, is connected. Then name it as voltage, right? This voltage series, voltage shunt, that right. So if the output is directly connected to the output, we call it voltage. That means your output is a voltage. So you shunt, you measure it by shunting. This tells you that if it is directly connected to the output, that means the output is a voltage. So this is basically, this is the output. Output is a voltage or a current. So what is it in this case? Since it is directly connected to this, in my case what we have is a voltage output, right? So therefore the feedback network is connected to the output. Terminal. In other words, one side of 10K resistor, RF resistor, is connected to positive terminal of V out. Therefore, it is voltage sampling. So it's a voltage sampling. So the output is a voltage. So therefore, we sample the voltage. So that gives me my output quantity X naught is actually my output voltage V. We need this because XF is beta times X out. X can be a voltage or a current. In this case, X out is a voltage. Okay? Right. The next thing is, so what we have is two cases. One is, this is the output. If the feedback resistor is connected here, that is the output, right. So we call this is the feedback resistor, feedback network. This is voltage sensing. In other words, output is a voltage. Now, on the other hand, if what I had was something like this, is this is where my RF was. So, the output is this. If this was the output, obviously then it is a voltage sensing, but my output is not that. This is my output, and if I had a feedback network there, right. So, this is my feedback network, that is my feedback network. If that is the case, we would have then called this a current sensing. In other words, output is a current. That is what you take and scale and give it to the input. If you had this particular arrangement versus this, we decide what the output is. So, this is x naught is V naught. If this was the case, x naught is I naught. Right. Right. The next step is number 3. If at the input, now this we have looked at the output now. Now input side. If at the input side feedback is connected to the input by directly connecting to input, name it as shunt mixing, okay, shunt. Else, so shunt means you are adding a current, right? You are adding a current. So, the input is, so in other words, input is a current. We add currents in shunt, we do not add voltages in shunt, right. So, the input type is current if you directly connect it to the input, else name it as series. What do we connect in series? To add voltages, right. So, that is input is a voltage. What that means is, if you have a input side like this, and if I connect my feedback directly here, this is a mixing circuit, right, mixer circuit. If this is the case, this is a shunt. So, this is the input, right. Remember what is the input? That is the input. I am connecting it directly at the input. So, therefore, this is my, so this is a, you are connecting the input and the feedback in parallel. You parallel connect so that you can have the currents like that, not the voltages. Here also the same, right. So, this is the voltage, this is the current. Or else the other way is, you have the input side like this and you connect the feedback not to the input, but somewhere else, not directly to the input. This is not the input, right, input is here. So, you connect it somewhere else, this is RF, this is what we call series mixing, or in other words, this is a current I in. This is in this case we add the two voltages. So, this is the V in and this will be my V f, right. This is this is the I, this is I in and this is my I f. Okay. This is I s or whatever that comes from here. This is the I in, this is I f. The difference is equal to, the addition of these two is equal to I s. I is basically the difference between I s and I f. Here V feedback is this, V input is this, actually V input, this is V s, what will become the V I is that will be your input voltage, okay, because you do not have to have that emitter resistor there for the input, okay. Get it? This needs to be very clear, you have to understand this very clearly. If you do not understand this, you will not be able to solve the problems. So, if you have any questions, please ask, we will go through it over and over again if necessary, right. So, therefore, in this case X in is I in, X f is I f, whereas here X in is V I and X f is V f. If you have this topology, all what you need to do is at the input you have to apply Kirchhoff's current law to find I f, I in. Apply KCL to find I in. Whereas here you have to apply Kirchhoff's voltage law to find the input voltage V I. The fourth step, so let us figure out for our circuit, for our example what this is, right. So, in our case this is where we connect it. Is it the input? Is the input? Are we connecting the feedback component directly to the input or somewhere else? Somewhere else. If it is somewhere else, we have to apply KVL to find that. In other words, this is a voltage mixing. In other words, we mix in series. So, therefore, mix network in this example is a series connection. In other words, voltage mixing. Right. So, therefore, what is XF? Before that, we will identify the topology. Now, with this we have the two things necessary to identify the topology. So, therefore, topology is voltage series, right. So, we had this and that. So, voltage series topology. Voltage series. Voltage series is the same as So, this is the output, this is the input. Voltage amplifier with series feedback. That is why we call it like this. So, therefore, input is a voltage, output voltage. This is the same as input is series, and you measure the output in shunt. So, this is series shunt topology. Series shunt topology is the same as voltage series, right. So, I said there is room for confusion here, because there are two types of naming conventions: voltage series, voltage shunt, and current series, current shunt kind of a method, as well as series shunt. So, remember what this is. In this case, this is the input and this is the output, mixing, right. Right. So, we now have that. Now, identify the XF. With that, we can identify the XF, because input type is the same as the output type. So, therefore, what we have is a output of the feedback type of voltage. That is why input is a voltage, Vi is a voltage, Xi is a Vi, like that. So, we have that. This is the voltage across 100 ohms resistor. That is this voltage. That is my this is Vf. Okay, that is my Vf. So, this is a place where a lot of students make mistakes, identifying the topology first. Now, right. Now that we have identified the topology, let us calculate the feedback factor beta. For calculate beta, which is equal to Xf over X out. So, in our case, beta is Vf over V out, right. We have identified both these. So, therefore, we can now do that. What is this? So, what do I have here? I have a network like this, V out, and I have 100K and 100. Sorry, 10K and 100, 10K and 100 ohms. So, this is RF and this is RE1, that is V out, and this is Vf. That is my network. Beta is equal to 100 divided by, so Vf is what? Vf is V out times RE1 over RE1 plus RF divided by V. So, that is the expression. So, you have RE1 is 100 plus 10K. So, this is equal to 0.0099, which is approximately equal to 0.01. So, we now know the value of feedback factor beta. Okay. Any questions? This has to be crystal clear, and the next step is even more important. These two steps are very important. Those two are the typically hard steps for the students. They are not hard, but clear? Everything clear? Shall we move forward? If you have any questions, please ask so that we can go over it again. Right. Now that we have these, we can now go to the step 2. Now, idea here is what we have is a complicated circuit here because we have signals coming from outside and connecting it. If we did not have this red color network, we know how to solve this, right? But because of this additional network, it makes analysis harder. So, what we are going to do is we are going to first find the circuit without feedback. If you know the circuit without feedback, because now what we are going to do in the next step is basically remove this feedback network and find the circuit without feedback. That is, we are basically going to find AV and RI and RO. That we know how to do already. However, there is an issue. If you just simply remove this circuit, right? Now, by connecting this circuit like this, when there is with and without this, it's without that is not actually the circuit without feedback. The reason is when you have a path like this, though the feedback may not be there, there is a current flowing through this. So, therefore, the impedance changes. For example, if you look at it from this side, let us say for example, if I have this connected to ground, let us say it is not connected to RE, but it is connected to some other maybe ground for example, then what you have as the output impedance is not what you had earlier. It is in parallel with this one. So, therefore, it has to be different now, right? It is not the same circuit that we have without it. So, therefore, in the next step what we are going to do is we are going to find the circuit without feedback, but with the effect of loading due to the feedback network. Okay? So, the next step, the important step is removing this RF, but removing in such a way that we still need to keep an eye on how much current goes through this and how much current goes through that at the input and output. That needs to be carefully controlled. Okay? So, with that we are going to draw it. Now, since we are almost out of time and this next step is extremely important, I think it is best if we stop here today and start from here on Friday, right? But if you have any questions on this part right now, this is the best time to clarify it, because I am telling you, you need to clearly identify what we are doing here, right? This is identification of the topology. That is extremely important before we go on to do anything else. Because if we wrongly identify a input as a voltage when it is a current, all your parameters will be wrong. If you identify your output as a current instead of a voltage, then your parameters will be wrong. You will be defining XFs and XIs and XOUts wrongly. So, therefore, for this purpose, it is very important to identify this, and also it is very important to identify beta. If you have beta wrong, 1 plus beta A is going to be wrong anyways, right? So, therefore, all these steps are important in order to make sure your answer is going to be correct. Right. So, let us stop here for today, and On Friday, we'll start from here and solve the problem. At the meantime, at home, we have the recorded video of this. I don't think we have a recorded video, but you have the lecture note, how we solve this. Go through it and see whether you understand what this means, okay? And when you come back next Friday, if you have any questions, we can start with that and then go into the next section, step 2, how to draw the equivalent circuit without feedback, but with the effects of loading due to feedback network. Okay, that's what we are going to start with on Friday. And that's the last lecture that we are going to do. So therefore, if you have any questions, please come up with those questions. All right, thank you.